So today we are going to discuss about the hydrate formation conditions. What are the reasons why the hydrates forms rapidly, how the hydrate formation is promoted, and what are the factors for that. So the primary factors for the hydrate formation is given here. So natural gas at or below the dew point with liquid water present. So that is the one of the important factor. No gas hydrate formation is possible if free water is not present. So the free water present is the compulsory thing for the hydrate formation. Second factor is the low temperature. Low temperature means at or below the hydrate forming temperature. If the temperature is low below than the hydrate forming temperature for the given pressure and for the given gas composition, then it is also the factor for promoting the hydrate formation. So third factor is the high operating pressures that may raise the hydrate formation temperature to the operating temperature. So that is the reason. Basically these are three reasons for which the primary reasons for which the hydrate formations are taking place. The secondary reasons could be high velocity or agitation or pulsation in the flow of the natural gas, the presence of small seed crystals of hydrates. If the very small crystals of the hydrates are present, then they also promote the hydrate formation, and also the presence of H2S and CO2. It's also add the basically the hydrate formation in the given natural gas. So these are the secondary reasons and factors for the promotion in the hydrate formation. Now come to the next topic, that is the prediction of hydrate formation. If any pressure and temperature, so gas composition is given, so we have to find out whether at this pressure and this temperature and for the given gas composition can the hydrate will form or not. So the information for the hydrate formation is very necessary, because normally the natural gas is transported in so many various pipelines, and we should know about whether the given operating conditions of that pipeline should encounter either in the hydrate formation region or not. So that's why we have a different methods. For example, one method is the approximate method for the sweet gases. Second method is the Katz et al. Method. Third is the Trakel-Campbell method for high pressure, and the next method is the MacLeod-Campbell method for the very high pressure sweet gases. So we are going to discuss about these four different types of the method which are used for the prediction of the hydrate formation. The first one is the approximate method for sweet gases. So how we can find the hydrate formation with the help of approximate method. So hydrate formation can be divided into two categories. So what are the two categories? Number one, hydrate formation due to decrease in temperature or increase in pressure. So if the temperature is down or pressure is increased, because of these two reasons, we know that there are chances of the hydrate formation. So this situation arises with no sudden expansion, such as in the surface line. If this is the region, then we can follow the figure 1 that can be used for the predicting an approximate pressure temperature conditions for the hydrate formation. So the second case, hydrate formation with a sudden expansion, such as in orifices and chokes. So in that case, we can use the figure 2 to estimate the hydrate formation conditions. So what are the figure 1 and 2? Let us take these. This is the figure 1. We have to use where the pressure are increasing or temperature are decreasing without sudden expansion. So if you see that x-axis is the temperature, y-axis is the pressure for the hydrate formation, and these are the different the gravity composition. This is about the composition. So pressure, temperature come for predicting the hydrate formations. So these are the lines for the hydrate formation. It means that suppose this is a 50 degree and this gas gravity is 0.6. So this is the, this could be the, say, about 500. So this could be the PSI. This is the pressure at which the hydrate formations are starting to form. So that's the basic concept here. If you see in the figure 2, where there are sudden expansion. In sudden expansion, see here, initial pressure in the y-axis 500 final pressure in the x-axis, and these are the constant line of the initial temperature. So initial temperature, initial pressure, these two values are given. We can find out the final pressure. So with the help of this value we can find out. But there are three parameters. If any parameter is missing, we can find out that one also. Now this is about, if you look about gas composition, that is not given here, but that is given here. This graph is used for 0.6 gas gravity. But what about 0.7? So for 0.7, this is the for the 0.7 gas gravity. So in this way we can find out. For example, this is one problem where the 0.685 gas gravity gas at 500 psi absolute and 100 degree Fahrenheit. So this is a condition for natural gas to what value the temperature can be reduced without the hydrate formation. That is simple problem we have to solve with the help of the figure 1. Hydrate will be formed. We can see here. This is a figure 1. So the data is given. If you remember that data, so we can just solve it very simply. So what the data is given? Data is given 500 pressure and 100 degree Fahrenheit 0.665. Okay. 100 degree, 500 pressure and 0.685. So if you see here, this is 0.6, this is 0.7. So there should be some line here in between this. Okay. Now the pressure is 500. So this is the 500 psi. And if you go there and just make downward, you can get that the temperature is near about 54 degree Fahrenheit. What it means? It means that at this pressure, for this composition of gas, the temperature for hydrate formation is 54 degree Fahrenheit. And now currently the temperature is 100 degrees Celsius. So we can say you can reduce the natural gas up to the 54 degree Fahrenheit. So that is basically the hydrate will form at or below the 54 degree Fahrenheit temperature. So in this way we can find out. Similarly, we can also find out how far can the pressure be lowered without respecting the hydrate formation of 0.685 gravity gas if it is initially at 1500 psi, and the second case is the 1000 psi at 100 degrees Fahrenheit. So we can go for both cases using the figure 2. So figure 2, if you use the figure 2, that is used for the 0.6 gravity gas, and we can find out at 1500 and 100 degree Fahrenheit the final temperature, final pressure will be 490 degree Fahrenheit. Let us look in the figure 1500 and 1000. This one is the figure 1500 and 100. That is the basically problem. So 1500 means this one, and temperature is initially, this is the 100. So we can say this point, and if you make the line, it comes around between around 500 final pressure. So what it means that if the initial pressure is 1500 and temperature is initially at 100 degrees Celsius, you can go up to the 500 psi. So that is the basic solution here. So in the case 1, it is 490 is given. Similarly, you can get for the 0.7 gravity gas at 1500 psi and 100 degree Fahrenheit, it is 800. So we can interpolate these two values to get the values at 0.685. At 0.685, the value becomes 753. It means that we can get the hydrate formation at this pressure. So you can lower the pressure up to this value. Second condition is 1000 psi and 100 degree Fahrenheit. Now see here, 100 at 0.6 gravity gas, 1000 psi and 100 degree. If you look here, so overall it is not intersecting the 100 degree. This one is the 100 degree. This one is the 100 degree. So it is not intersecting the 100 degree line. What it means? Similarly, this one is also not intersecting the 100 degree line. What it means? It means that the gas at these conditions can be expanded to any pressure without the hydrate formation. There will be no problem because the temperature is such a high temperature. So you don't worry about it. You can expand this gas at any pressure. So this is all about the first case.